All right. I'm Michael, and today I will be talking about PyTorch 2.x series export path. So this is more of a directional thing that we plan to launch in the coming major versions of PyTorch. So what is PyTorch 2.0 export? It's a workflow for whole graph capture and optimization that's using the best technologies that Peng and Jason and Sumit talked about that we are using to bring compilers to PyTorch in order to provide an explicit whole graph capture workflow. So why do we care about export? I mean, we talked a lot in the previous talks about sort of rich out-of-the-box graph capture, but we know that our most demanding production users typically want granular control over performance and runtime behavior. So for example, users with hard latency or resource utilization budgets tend to want ahead-of-time guarantees that certain optimizations will be performed, and they don't want dynamic compilations necessary in the loop. As another example, we have a lot of users that operate in fairly constrained runtime environments. Python might not even be available. So for example, if you're running on an embedded system or on a phone or in a C++ only inference environment, Python might just not be available. So for these users, we plan to provide an export workflow, which utilizes the core technologies of PyTorch 2.0 to produce a single graph ready for a downstream system. And that's the third major use case for export, which is that we want to interoperate with a vibrant ecosystem of backends. And that means we need to meet them where they are, which is generally providing a whole graph that represents the compute for a single model. So there are three components that we want to deliver as part of this vision. So first is the whole graph export API that we've been talking about, which leverages the latest graph capture technology in Torch Dynamo to soundly and easily produce a single graph out of your PyTorch model. The second is that we really want to focus on simplifying integration with PyTorch by standardizing our graph representation on a smaller number of operators with well-defined semantics. So this is the primitive operator set that you've heard people talk about today. And lastly, we want to provide tools for working with and transforming graphs so that folks integrating with PyTorch don't have to reinvent the wheel every time when they want to do basic compiler transformations. So first, for some background, I'm going to describe a little bit about what we do in PyTorch 2.0's default mode, which for the purpose of this talk, I'll call the just-in-time or JITted mode. Now, this API is already a little out of date. We're moving kind of fast in PyTorch land. So Torch Dynamo optimize is really Torch compile now. But when you call an optimize function, Torch Dynamo performs a sort of bytecode analysis of the program and creates an optimized representation, which intersperses partial graphs with Python code. And it then attaches guards to this optimized representation so that if you call the same function with materially different inputs, say now your tensors are on a different device, Torch Dynamo will transparently recompile the graph. So you always get correct results. So there's a lot going on under the hood here, but this is how we can provide the sort of magical default experience of PyTorch 2.0, where you can add just a single line of code to your program and get significant performance improvements with no manual intervention, no tweaks to your code, et cetera. And we're confident that the majority of PyTorch users will really love this workflow. You get performance without compromising the fundamental user experience of PyTorch. The export stack allows you to capture your entire model as a single graph. So whereas previously you had sort of this interspersed partial graph and Python code, here we just export a single graph with the sort of assumptions made by that graph. Hey, my tensors are on GPU, or my tensors have a particular set of shapes or vary along dynamic batch length, et cetera. And any assumptions the model is making will also be returned for inspection by the user. So unlike Torch compile, this workflow is explicit rather than implicit. Sometimes Dynamo doesn't know how to represent something in the final graph. Say you have like an async generator in your model or something. And in these cases, you may be required to change your model code. However, in practice, we find that the majority of models that we're seeing on our benchmark suites can be exported cleanly to a full graph. So that's the export API. But what are we actually exporting? One of the historical hard problems that backends have faced when integrating with PyTorch is that PyTorch has over 2,000 operators, and historically we've lacked very good sort of guarantees about their semantics. Right, so here's a figure from Horace, which I believe we already have, like maybe we've spawned like 400 more operators in this time. But this is sort of a breakdown of all the operators within PyTorch, and there's a great amount of complexity. And so if you want to support sort of every operator in PyTorch, it's historically been an almost insurmountable task. So our response to this is we want to greatly simplify our operator set, which is called A10 if you don't know, and we want to make stronger guarantees about their semantics. So one example is we want to greatly reduce the number of ops by eliminating variance. So add out, add underscore versus add. And we want to express some of the compound ops in terms of decomposed, smaller constituent ops. So we can produce a subset of ops that's a lot easier for a backend to handle. And you go from 2,000 plus to around 750. This subset also has fundamentally simpler semantics. So A10 and PyTorch are typically quite expressive, so you can do sort of in-place mutation of tensors, you can do striding, et cetera. But in this simplified subset, all of our ops are purely functional, tensors are always contiguous, et cetera. And this allows us to solve some of the problems that we see backends repeatedly running into when modeling PyTorch. For example, how to deal with tensor mutation, or aliasing, or striding. The export system will ensure that these are not present in the exported graphs, but retain the sort of soundness properties of the graphs themselves. So overall, we think that this will greatly simplify the task of writing a backend for PyTorch. And we also want to provide sort of guaranteed metadata information. For example, what is the shape and device and D-type propagation of any given operator, so that each individual backend doesn't have to construct their own sort of lookup table for this stuff. We can provide it sort of canonically correct within the Torch library itself. And for sophisticated backends that want even more control, and Jason talked a little bit about this, we can further decompose operations to a so-called primitive operator set. That's just 150 to 250 ops with very, very simple semantics. So in this case, a lot of the implicit behavior of PyTorch operators, like promoting different tensor types, broadcasting shapes, can be made explicit. And our goal here is to achieve functional conformance as a PyTorch backend. You really only need to implement the set of primitive ops. And this makes it a lot easier to bring up a new backend on PyTorch. Now, obviously, if you're decomposing your entire model to this really small set of ops and you just sort of ran them naively one at a time, that would be pretty slow because there would be a lot of per operator overhead. So this is mostly intended for sophisticated compilers that can reclaim the performance via operator fusion. But it is a sliding scale, right? You can choose whether to decompose an operator from the sort of A10 level, the closer to eager level, into the primitive ops set, so that you can start by implementing first the primitive set of ops, and that guarantees sort of, you can run any PyTorch model. And then slowly you can sort of implement more of the higher level eager ops to get back performance that way. We also want to provide utilities and common functionality to make it really easy for people to work on the graphs that they're getting out of this system. So right now, getting your code out of PyTorch into a backend requires a significant amount of custom work. Every backend acquires the graph and works with it in a slightly different way, and we see a lot of people reinventing the wheel when it comes to common compiler passes, like dead code elimination, common sub-expression elimination. They write their own pattern matchers, et cetera. So we want to make it as efficient as possible to map this exported A10 IR onto any backend. And so we want to provide a set of tools and functionality and infrastructure to allow people to do that. So just to recap, for PyTorch 2.0 export, we want to provide a whole graph explicit export API that lets you get a sort of freestanding graph out of any PyTorch model. We want to standardize our IR and operator set so that it greatly simplifies the task to bring in a new backend. And we also want to consolidate our compiler infrastructure to avoid every backend reinventing the wheel. And by doing this, we want to foster a really vibrant ecosystem of separate backends. And for us, significant functionalities in Tree now, the APIs that you saw on this slide are not final, but they are available in the nightly. And we plan to stabilize this functionality and make it generally available in a follow-on release from 2.0. Thank you, everyone. And now Horace, I believe, is going to talk about our support for dynamic shapes within the whole PT2 stack.